Thank you, the workshop team, Maitri, and everyone, Zuyao, for inviting me and to discuss what is a very interesting topic, a hot topic for the industry, and also a hot topic for research. Rarely has a topic covered all aspects, right? Immediate, future, and in between. All researchers and industry are all very much into heterogeneous integration. And today I'll talk about multi-chiplet heterogeneous integration packaging for semiconductor system scaling. And upfront, I would like to say that this presentation is a summary of the work that is done by a big team of researchers here at IME, and also the work done with our industry partners in our consortia projects. And so this is the outline of my presentation. I'll talk about how the semiconductor systems are getting diversified and how heterogeneous integration is driven by diversified semiconductor systems. And then such semiconductor systems need to be scaled. And to do that, multi-chiplet heterogeneous integration packaging is the way to go. And I'll talk about the platforms, and also the purpose of my presentation here is to show you how different applications are driving heterogeneous integration to provide customized packaging solutions. And the three main platforms, I think each of the previous speakers talked about it. We use slightly different terminologies, but what we are talking about is similar, fan-out wafer-level packaging or interposers or 3D integrated chiplets, 3D IC for short, okay? And so if you look at the history, in the past, singular applications drove semiconductor system development and manufacturing. Mainframes followed by PCs and then smartphones, which was done through, earlier on board level integration, and of course SoCs with monolithic integration drove the PC and the smartphone era. But now, today, diverse and rapidly growing markets demand application-specific power performance, form factor, and cost optimization, and this cannot be achieved by chip and board scaling, and package scaling becomes very important. So in the future, package integration is very critical, and I would like to look at package integration as the third vector of system scaling. So what is system scaling? Really is a realization of the systems through optimization for power, performance, cost, and form factor. So we talked about chip scaling as well as board scaling, and the three kind of vectors I talked about. If you look at today the system on chip challenges, as again my previous speakers talked about, the cost of realizing a system on a chip is very high. That's known. The performance of the system on chip is limited by the size of the reticle itself. So you're limited to one reticle size. So that's one thing. If you look at the system on the board, it tends to be higher power consumption due to longer PCB traces. And the PCB does not necessarily always have the best form factor. So when you look at power, performance, cost optimization enabled by multi-chiplet heterogeneous integration packaging, it addresses both of these limitations of the system on a chip, of performance and cost on the left side, and the power and the form factor on the right side. So that's why, again, that's one way of looking at it, but that's what is driving multi-chiplet heterogeneous integration packaging. And if you look at, let me activate the mouse, the laser pointer, that is. This comes in different formats. You have fan-out wafer-level packaging, you have interposers, and then you have 3D integrated chiplets. And I will talk about in the rest of my presentation how different applications are driving each of these multi-chiplet heterogeneous integration platforms. So I'll start with the embedded high-density fan-out, followed by interposer and 3D integrated chiplets. So this is the overview. If you look at the target applications, 5G, millimeter wave antenna, automotive radar, to a certain extent, we believe optical engines are all driving fan-out wafer-level packaging because it provides a cost-effective solution without having to break the bank with, large interposers or with 3D stacking. For data center, high-performance compute, and AI, where the goal is to shrink what was on large boards into smaller packages, manageable packages, interposer is very important because it enables integration of multiple chiplets on a single platform in much smaller form factors and at lower cost compared to SoC sitting on the board. Now, the SoCs themselves need to be disintegrated and reintegrated, and that's where 3D integrated chiplets come in, wherein a single large SoC can be broken, in this case, just for sake of discussion, into 3 chiplets that are reintegrated here through hybrid bonding or many such technologies, very super fine pitch microbumping or hybrid bonding to form 3D integrated chiplets. So you have the traditional bumping here on this chart out here, and then you go into fan out, 2.5D interposer, and 3D integrated chiplets. The interconnect density per millimeter square, you can see, goes up by orders of magnitude as you go up through fan out and interposer to 3D integrated chiplets. So it's 5x to 10x from bumping to fan out, 10x from fan out to 2.5D interposer, over 100x from interposers to 3D hybrid bonding. So the real challenge with heterogeneous integrated, multi-chiplet heterogeneous integrated packages is to choose the right package architecture, design it, choose the right materials, and then have design flows and process integration flows that enables you to achieve power, performance, form factor, and cost optimization. So I'll start with embedded fan-out. Fan-out wafer-level packaging embeds chips in the epoxy mold compound to form what is known as reconstituted wafer. The embedded chips are interconnected using wafer-level redistribution layers. You can see these redistribution layers connecting the chips. These fan-out packages can be mounted directly on the PCB without a packaging substrate. They can be up to 25 millimeter in size. So there are many ways of creating a fan-out package. First is what we call the mold-first approach, and the other one is the RDL-first approach. I show the picture of a reconstituted wafer here. You can see there is a mold compound with many chips that are embedded inside of it. So when we talk about the mold-first approach, what we do is we pick and place the chips face down, and the wafer-level epoxy is applied and molded to form the reconstituted wafer. It's debonded from the mold plate, turned around, and we apply redistribution layers. So the molding is done first. We call it mold first. And then the package is singulated here. And due to wafer warpage, etc., the pad pitch is typically greater than 100 micron, RDL pitch greater than 10 micron, and less than 3 RDL layers because this wafer tends to warp. There is no carrier wafer here. In the case of RDL first approach, we call it kind of high density fan-out wafer level packaging. You start with a sacrificial layer, in this case, a glass carrier. Multi-layer RDL is first formed on the glass carrier. Subsequently, chip-to-wafer assembly is done, like a flip chip on wafer. Then we do a epoxy molding, and then carrier debonding, and then package singulation. Of course, finally, there is going to be the bumping process, which enables it to attach to the board. So the chip I/O for microbump, in this case, with RDL first, you can do microbump pitches of up to 50 micron. RDL pitch can go to 4 micron. All of this because the RDL is first formed on a glass wafer, pretty flat, and we can go up to 7 RDL layers, making for very complex interconnections. And I will go through examples, applications wherein we use both mold first and RDL first in the subsequent slides. So in millimeter wave systems, hope you can see the banner of my slides. Okay, I cannot hide it. Okay, there it is. Okay. In millimeter wave systems where the signal frequency is over 30 gigahertz, it's important for the antenna to be close to the millimeter wave chip. Up top here is shown a conventional case wherein the antenna is on the board and the chip is attached to the board itself. You can see that there is a longer signal path that tends to cause significant losses of signal and higher power consumption. So what we propose is a double mold structure wherein the lower mold compound hosts the millimeter wave chips, and then an upper mold compound is there, which hosts the antenna, and in between there are RDL layers. The ground plane is there to ensure that the antenna is designed properly, and also that the chip doesn't get in the way of antenna operation. So this kind of a packaging structure is quite suitable very suitable actually for 5G, 6G, and WiGig applications. And this is what we call as the antenna in package realized by fan-out wafer level packaging. I show the process flow out here. You start with a mold plate with the MMI chips face down, and then they form a reconstituted wafer. And then we debond the reconstituted wafer and apply the RDL and attach it to a carrier wafer. As you can see here, it's flip attached to a carrier wafer, and then we form through mold vias, following which we form the ground plane. We form the ground plane, and then a second mold layer is formed, and then patch antennas are formed on top, and then singulated can be attached to the PCB. This shows the cross section. So a lot of optimization goes into the choice of the epoxy mold on top and then the bottom, and how the process is integrated to ensure there is reduced warpage, etc. And so this shows the result for 79 gigahertz automotive radar application, wherein this structure enables the fact that we are making the ground plane in between these two mold layers, enables a significant reduction of the insertion loss, as well as adequate bandwidth for this antenna operation. And this is something that this work was done in a consortium project in IME with the industry partners, and some of the work involved is related to optimizing the dielectric properties, the decay and the loss tangent, to ensure the antenna performance is good, as well as that is for the top mold compound. At the same time, both the mold compounds need to ensure that they meet mechanical warpage and stress requirements. This is a case wherein we did the antenna in package for 60 gigahertz application. This is for more like a WiGig, and we were able to demonstrate the reduced package body size and RF performance and the reliability, as you can see on the left chart. We believe this can be extended up to 300 gigahertz in 6G applications and even for sensing, and that's where a lot of the focus in IME is right now. Next, move on to another application for fan-out wafer level packaging. This is in optical engines. In data centers, in data centers, the top of the rack board is where the top of the rack system converts optical data into electrical data that is processed by the top of the rack switch. So the optical data comes in from between racks as well as from the different servers within the rack. So this optical data today is converted into electrical data by pluggable large form factor, larger form factor pluggable optical modules that drive copper traces along the top of the rack board onto the switch. The switch acts like, I would guess, like a it routes these packets from one server to another, from one rack to another, and one data center to another. So this large copper trace is driving the large copper trace is what is making this very power hungry, the pluggable optical module. So one of the solutions that the industry is looking to is co-packaged optical engines, wherein this pluggable optical module is reduced in form factor to sit on the same package as the switching device itself. So one can reduce the power consumed by this significantly. And typically, the optical engine, in this case, I show it uses a photonic chiplet along with electronic drivers and amplifiers that are formed using silicon germanium technology. This is a photonic chip, and there is laser diodes also, which can be outside the optical engine, or it could be inside integrated on the photonic chiplet. So such an optical engine, as we call, can be formed using fan-out wafer level packaging. And this is a very good case of multi-chiplet heterogeneous integrated package, which will be needed even more in the future as we move to co-packaged optics. So here I show the actual optical engine that has been realized using fan-out wafer level packaging. It integrates the PIC and the drivers and the transimpedance amplifiers in this format. And the red line out here is the path between the switch all the way to the photonic chip. The switch drives the signals through this package. The signals are at 100 G per lane. It's quickly moving up to 200 G per lane. And this fan-out package with the through-mold via can do that. And this package enables the driver to drive the PIC directly with minimal losses. It's sitting right on top of the photonic chip. And the insertion loss between the switch all the way here is less than a half dB. An integration flow like this is another IME demonstration working with the industry partners to enable them to, in the future, reduce power consumption from over 20 watts in a pluggable optical module down to below 5 watts, to around 5 watts or so. So this is at 800 G. Pretty soon, the requirement is coming up to 1.6 terabit per second and 3.2 with 200 G per lane. And we are having a paper in the OFC conference coming up later in March, wherein we show 200 G per lane with a fan-out package successfully supporting this optical engine. The process flow for making an optical engine is shown here. You can see here the PIC is face down on a mold plate and over-molded. Then you flip it and you process the RDL layers, and then a through-mold via is also formed at the same time. So finally, what we do is we dice this molded wafer, both the mold compound as well as the PIC, through the trench to expose the optical waveguides, and then we can do the fiber attach, as well as attaching the EIC, the driver or the amplifier chip. So this process flow meets optical coupling specs in a 9 by 15 millimeter package, capable of, in this particular demonstrator, it was an 800 Gbps package with very good coupling loss. Of course, we need to do better, but this was the preliminary results at under 2 dB optical loss. Sorry about that. I'll go to the next slide now. Next, I talked about optical engines in the past. I'll now move on to RDL first approach that we have taken up for multi-chiplet neural net perception accelerator. And as was again seen in the previous presentations, making new SoC for rapidly evolving neural net models is really expensive. Instead, a modular chiplet-based approach is ideal for such applications, wherein you can increase the number of chiplets depending on the model size. So what we did was we set out to do a demonstrator vehicle, in this case, with 4 chiplets that were fabricated in 22 nanometer CMOS. And these chiplets were interconnected using the advanced interface bus. using what is known as the Intel's EMIB process. And now we wanted to see if RDL first approach can be applied to this package. So this demonstrator used 4 chiplets connected by advanced packaging, in this case, RDL first fan-out wafer level packaging. The we used a 5-layer RDL first package here. As I pointed out earlier on, we can put up to 7 layers because we start with a glass carrier on which the RDL layers are formed. And these chiplets are interconnected with excellent signal integrity, as you can see for the advanced interface bus. This was you can see a smaller package here, 13 by 14 millimeter by 14 millimeter, accommodating 4 chiplets. And the results were very encouraging. This was published in the VLSI Symposium a couple of years ago. Peak efficiency of 7 tops per watt at 0.6 volt. And what it showed to us packaging folks was that RDL first can indeed support a variety of chiplet interfaces. We did this for the AIB, and our design calculations indicates that we can support the bunch of wires as well as the UCIe express using RDL first approach. So the conclusion of this work was that really that by integrating an optimal number of chiplets, we show 4, it can be expanded with a 25 millimeter by 25 millimeter package. You can see that can easily be expanded to up to 16 chiplets. It enables a modular reusable approach to support the chip requirements to support changing neural net models. So I'll now move on to the interposer. I hope I'm not running out of time here. The purpose of the interposer, as was again seen in the past, was to see what was on a large system board to bring it together on a smaller interposer so that when you go from exascale to zettascale systems, you can have many of these interposer packages as building blocks. So it can accommodate multiple chiplets with very fine micro bumps. We all know that. At IME, we have multiple options to create the interposer. We have a passive interposer, very well known in the industry. We also have demonstrated an active interposer, as well as embedded fine pitch bridge interposer. And I'll go through it quickly. The passive interposer is something that's very well known. It can go up to 3x or 4x the reticle size, used to interconnect memory and different FPGA or processor unit chiplets. I will not go through this. One of the biggest challenges that the industry faces is, as the size of the interposer goes up, the cost is becoming a real challenge. Another way we have done interposers is by using splitting off the I/O circuits as well as decoupling capacitors and form them on a mature node wafer and do VLAS processing to create an interposer, and then have an SoC or an FPGA which has got only the core transistors, and then have them attached on an active interposer. So you pull out these thick oxide transistors from leading edge CMOS and then transfer them to the interposer wafer. It could be a 65 nanometer. We showed it using a 130 nanometer wafer, and we were able to demonstrate I/O and analog functionality. Another functionality is analog circuits. DACs and ADCs can also be transferred down and kept in close proximity to the logic functions that need to work with them. So this is something that we have realized using foundry wafer as an interposer wafer. So as silicon interposers have as much as they are being used, they have become an expensive option for 2.5D integration, especially for large interposer applications. And the industry is exploring alternative approaches. And we, a few years ago, demonstrated what we call as the embedded fine pitch interconnect bridge interposer. So here in the case, the bridge, of course, gives short, dense, fine pitch interconnects, while the RDL on the top gives you long, high-speed interconnects. That's the approach. This is the process flow for it. We first use the RDL first type of an approach, wherein on a carrier, we form multi-layer fine pitch, multi-layer RDL, followed by fabricating these pillar structures, which in the future become the via. And then you have a bridge also to, in the future, connect. We flip it around, place it on another carrier, and we are ready to attach the GPU and the memory on it. And this is how a bridge interposer works. So we have demonstrated it for 1x and 2x reticle. The real challenge now is to go and see, can we do up to 4 reticle or even 6 reticle sizes to enable it to accommodate larger systems. That's the real challenge right now, and we are working on it. This is some of the results earlier on that we have had with the bridge interposer. Can see that the bridge can easily accommodate the interconnect between a high bandwidth memory and a SoC here. This is a cross section showing the 2 chips that are interconnected using a fine pitch bridge here, and then the TCOB testing showing it to be successful. I mean, it's a viable option. And now I'll quickly go to 3D integrated chiplets. Now, a lot of people say, like, why? One of the questions that comes out, why are we going into hybrid bonding? On the left, what I show are solder-tipped copper pillar microbumps. And on the right, I see solder-free hybrid bonding. As you can see here, as the pitch goes from 50 micron down to below around 20 micron, the protrusion, of the solder after you form thermal compression bonding can result in bridging of the solder. That's a big problem. So that limits copper pillar microbumps with solder tipping. So the industry has, of course, has started to use solder-free hybrid bonding. As you can see, there is no bridging of solder in this case because there is no solder. And you get direct copper and oxide bonding to achieve sub 10 micron pitches. Got both wafer to wafer, which is particularly helpful for memory type of applications and backside illuminated imager type of applications. A lot of the work here involves in how you activate these wafers before they are attached and how you clean them. There's a lot of know-how that IME has developed in this area to enable high-yielding hybrid bonds. You can see that with a linear IV curve here across a large number of daisy chains. Same thing with chip-to-wafer hybrid bonding. It's important to have particle-free dicing, CMP uniformity to ensure that the copper layers, when they do the hybrid bonding, they are effectively bonded with no defects. So that's about wafer-to-wafer and chip-to-wafer hybrid bonding. And a lot of the work we do is looking at what does it take to convert a large SoC, break it down into smaller chiplets, and reintegrate them to form 3D integrated chiplets, or an SoC becomes a 3D IC implementation. And that's where a lot of the focus is. So now we looked at fan-out wafer level packaging. We looked at interposers, and now we looked at 3D integrated chiplets to solve all of these different problems. So one of the challenges that we see with 3D integration is thermal cooling. When you integrate high-performance chips one on top of another, how do you take the heat out? One way of doing it is, in IME we are exploring, is forming micro pin fins on the backside of the active chip itself, and then do embedded two-phase cooling. You send the liquid in, it converts into gas, and then you take it out. And it's a pretty complex approach, but we think that it holds the key to realizing high-performance 3D integrated chips with up to, in this case, with flow rates of 70 milliliter per minute. We have achieved heat flux of up to 200 watt per centimeter square with a maximum chip temperature of 70 degrees centigrade. So this is a novel approach. Probably will need few years before the technology readiness level will mature up to where the industry can use it. But this is we believe is pretty critical to achieve high performance 3D integrated chiplets. So when we look at all of these technologies, what's the future hold? This is an older from TSMC, with a few 100 billion transistors. today we are in the world of exascale computing. As we go to zetascale computing, we need to have packages that go up to 1 trillion or even exceed 1 trillion transistors within the package. And an example of when such a package is needed is where today you have multiple GPU boards with high bandwidth memories, all of them having high speed links that are together connected by pluggable optics. In the future, you would need large interposers with stacked GPU chiplet or XPU chiplets, stacked memories, and optical engines to take data out, large amounts of data out of this package. So you can imagine what was supported by many 5 or 10 boards, or let's say a few boards, being supported within a package itself. So critical to realizing that is, as I show in the next slide, hybrid bonding will enable you to do 3D stacked chiplets for memory as well as XPU. Could have fan-out or TSV packaged optical engines that take large amounts of data in and out of this package, large bridge interposers that can interconnect all of these together. And last but not least, we need to have heterogeneous thermal solutions that take heat out of over a kilowatt of GPU, and then making sure that the high bandwidth memory is not impacted by these kilowatts of GPU, and at the same time the optical engines can work at the right temperature. So these are the challenges that need to be now addressed when you go from the world of exascale to zetascale. This is the challenge that faces us. And this is the summary of my presentation now. Market growth, as you saw, in diverse markets is driving the adoption of multi-chiplet heterogeneous integration packaging. It's a must-have toolbox. In addition to device scaling, device scaling will continue to go on, but heterogeneous integration is a must-have. With multi-chiplet heterogeneous integration is a must-have toolbox, and continued innovation across the ecosystem ensures availability of broad and deep, sophisticated new capabilities in MCHI. I talked about, fan-outs, interposers, and 3D integrated chiplets. And as I showed in my previous slide, bringing all of these things together as we go from exascale to zetascale systems is super important. That's the challenge on our hand. And I think the industry is gearing up and will be successful to do this. Thank you.